catching us up on schedule too, and for a very interesting presentation. Here, what I'll do now is just shift off this, and our next presentation is from Peter Handel from the University of Missouri at St. Louis campus. There's been a lot of discussion and exchange, and I recently learned of Peter's interest, so thank you very much.
Thank you very much for your invitation, and want to try to get this on the screen now. We need to
possibly
close it once and start it again. Let's see, okay. Just closing and opening may take care of it.
Looks like it did. Great.
Yeah, there we go. Okay. A trick that was told to me by, or given to me by my son, who is at Apple Computers since about 6 years. He's at the headquarters building. So if we try to get a car, as we heard at the last talk, that starts when it's supposed to start. And we get something that's perfectly reproducible. Then we have to understand where a lot of the excess heat comes. And that is in fact a new phenomenon or a new effect, if you want to call it this way, which I call the thermoelectrochemical effect. And in the other cells, the ones with the circulating electrolyte, including also the Patterson cell, it's that thermoelectrochemical effect connected with, but also including the the effect which I call the thermoelectromechanical effect. So we'll discuss the phenomenology, the types, these two effects, particularly the first one I'm going to discuss in this talk. And give the excess heat formula and compare it with the experiment. See also the literature a little bit. All right. In general, excess heat power is proportional to the current, as we have seen, as I have attracted the attention of the audience here in slide number 9 of Dr. Storms, and I'm sorry, the number 13 of Dr. Storms, and number 9 of Dr. McCuber. In general, it's proportional to the current. Some non-uniformity is due to the exothermic and endothermic sections of loading characteristics and runaway effects. All of these effects have been studied by me in detail together with Professor Dr. Ahlefeld in Germany in 1967, 68, 69 in Garching. And we studied the phase transitions of hydrogen in platinum, palladium, and so we started with a good understanding, and when Pons and Fleischmann in 1990 disclosed their observations, I was one of the believers. I always remained one of the believers, and I was particularly angry when I saw the ridicule that honest experimentalists are subjected to, people who just put into question their character instead of better looking and trying to understand nature better. and look for a deeper understanding of the phenomenon. And that also explains the fact that some people observe it, some people don't observe it. So here we have a thermoelectrochemical effect explanation in a electrolytic cell. As we notice here, there is an input of energy. E cross H is the Poynting vector integrated over the surface. It gives us the voltage times the current, which I guess this is a pointer, or no? Anyway, pardon? I'll use the pointer that's present here, I guess. Okay. So I think it's visible, a pointer here. So what's happening is that when current flows through, the electrons which come in are not identical with the electrons which come out. In various experiments, the adiabatic surface, this means the isolating sheet of the calorimeter, was either of the type of this surface A, where the platinum and the palladium, either the rod or the corresponding wire being of the same material would go through, or of the type B, where people made connections inside and made, for instance, connections in order to save on platinum and palladium. These were the guys, the misers were the guys who were unsuccessful and never got any excess heat. And so the interesting thing is that these electrons are not the same. In fact, each electron has a backpack, and in that backpack it carries a certain amount of heat. The entropy per carrier, the entropy carried by one carrier, is known as the thermopower, or the Seebeck coefficient. And it is different in different materials. This means there is, if you want to speak in terms of the language that's going to be useful to understand the excess heat, one important excess heat component in circulating electrolytes, then we can speak about the solvatation energy, or the dressing energy of the electron as a particle in condensed matter. And so in this case, therefore, what we observe is that in fact what is important is the value of the Seebeck coefficient at the point where the current, electric current, passes through the adiabatic surface, passes through the insulating wall of the calorimeter. And so you would understand a lot better what I'm talking about if you would allow these two rods to touch inside the electrolyte. Everybody would jump high as the sky, or as the ceiling here would allow, and would say, well, I know in that case when they touch, I have a thermocouple. I have, of course, in that case, the thermoelectric, well-known thermoelectric effects. Every housewife uses a thermocouple to find the temperature of the roast. So what I have, of course, then is a generation of current when there is a temperature difference, and on the other hand, when there is a current passing through, there is the Peltier effect. And we know a lot of people in the US have these heat pumps, and I always like to give the students that problem where they were very happy at the end when they were able to see when the temperature difference is not so high between inside and outside. With the heat pump, you can get 10 times more heat in than what you pay to the Union Electric or American UE company or to any of the other 40 companies that are paying money into EPRI. And by the way, Tom Passel, when I first presented this in December 1993 in Maui, afterwards, the month after that, he flew right away to St. Louis, and I invited him to the rotating restaurant. He said, "Peter, keep it quiet for a while." "I will keep it quiet," I said, "and I will present it in a way that is absolutely corresponding to the subject. I don't want the funding to finish because I am certainly convinced that there is a good chance that we can obtain indeed non-muonic cold fusion, controllable cold fusion, non-muonic cold fusion. And indeed, I think that this is a possibility today more than ever, particularly because of these encouraging results that have been presented here. And so, continuing with this, I just want to show the literature that showed the work in cavitonic hot fusion, together with Professor Schneider also in Florida. And then the work I did, I tried, of course, initially to explain the cold fusion result, the heat, the excess heat, by calculating the tens of orders of magnitude that can be obtained in increase, but still way too little, by taking into account the potential barrier for nucleation of hydrogen bubbles at the surface of the electrodes, or deuterium bubbles. But then in Maui I presented this, and in Zeitschrift für Physik I've published in 1994 the detailed description that I'm giving you also here. The energy current density and current density in any condensed matter situation are given by these expressions, where W and J are energy and charge current densities, pi, the Peltier coefficient, mu, electrochemical potential, E, the electronic charge, kappa, the heat conduction coefficient, sigma, electric conductivity, and this computer, this laptop is also a miser, as we notice, and tries to quit on me. S is the Seebeck coefficient, and sigma the electric conductivity. So, in open cells, I call it the thermoelectrochemical effect. In closed cells, the thermoelectrochemical effect. The closed cells are the ones that use some platinum wall in order to catalyze the recombination of oxygen and hydrogen inside. And then the ones with circulating electrolytes, I have done the theory there also, didn't care to publish it. I hope that at least I get some money for Motorola, because I saved them some patent expenses for Patterson. But Miley called, and already I had intimated to him what the situation is there, and so he called, and I got no money from there either. And so I just want to say what we are dealing with is the following. The applied voltage, U, is the sum of the voltage necessary to create oxygen and hydrogen. That is, in fact, the thermodynamically calculated EMF of the galvanic element. The net work done is the work done, J is the current and U is the total voltage, minus the 1.54, this means the cell EMF. And that's the network. Why? Because the gases that are generated can be used, for instance, for all kinds of purposes. They can be put, in principle, to into a electrochemical cell and a fuel cell, how we call it, and generate electricity again, and that can be recirculated and used. And or actually, it may be more precious for us to have it as as hydrogen and oxygen. And so what I want to say, the network is given by that expression. The overpotential is a dissipative, corresponds to a dissipative phenomenon at the surface of the electrode. The Tafel law gives the overpotential. And in the limit of very small currents, we can, the alpha here is the fraction of the overpotential dissipated or exhibited at each of the two electrodes. This alpha is between 0 and 1. And in the case of small currents, we can expand the exponentials and we get this expression which tells us that the overpotential goes to 0 when the current density goes to 0. And so the thermodynamic efficiency of the engine is equal with the work given to the system divided by the heat given to the system. S is the difference of the Seebeck coefficients of the two electrodes, and the excess heat coefficients is given by this expression, is 1 over eta 1 minus 1 is equal with the heat that shows up unexpectedly in the cell, T0S, where S between brackets is the difference of the Seebeck coefficients between the electrodes, but mediated between the outer surface of the insulation of the calorimeter and the inner surface. So I consider the middle plane of the insulation. So that's why there are these brackets around S here. And I'm putting it in this form, but you have to imagine upstairs and downstairs an additional factor of J, the current, which I simplified. And that's why it looks not so easily recognizable, because it doesn't have the dimension of a work, neither upstairs nor downstairs. But if you multiply by Jt, T is the time in which you operate the cell, the current, J, then you get energies. And so we can put it in this form here, but here I actually made a mistake, because it's not U minus U0. I'm sorry, I didn't make any mistake, but I think if I would have had the mistake, the energy downstairs, it would have been mistaken. This is already voltage, so it is energy divided by the time and by the current. Okay. This I call the thermoelectrochemical effect in an open cell. And we notice that this epsilon in the reversible limit, when, oops, I'm sorry, when the dissipative effects go to 0 and the temperature difference goes to 0, this means when the temperature difference goes to 0, then this S, the difference between S values times the temperature difference, the temperature difference between inside the calorimeter and outside goes to 0. Then downstairs we have 0, and so we obtain infinity. So even for a finite time interval, we get infinite excess heat. But on the other hand, we may also include, if we want, the energy released in the platinum wall, in the catalyst, if we put in a catalyst there. And in that case, of course, we would get a finite and much smaller excess heat fraction. And, but this is a fake or incorrect, because we expected that heat anyway. It's not the true excess heat ratio. And here we can see, in the case of the various electrodes used, of course we can make a connection inside to a copper connector. For one experimentalist may have chosen to save only on the platinum, and so made a connection already inside there. So the various people get different thermoelectrochemical coefficients corresponding to pi. I think I convinced you already that the presence of the electrolyte between the electrodes does not change the amount of excess heat. So, in the case of Pons and Fleischmann's cell, we obtain similar percentages, 23, 19, 5.5. And so I just want to thank you for your attention at this point. Want to mention that, of course, the thermoelectromechanical effect, which comes from the solvatation energy of the, for instance, the sodium sulfate, what we have in some cells, or whatever electrolytes we have there. Its dependence on temperature creates a similar heat pump like we have seen in this discussion that I presented here. And as far as the conclusions are concerned, subtract in open cells the thermoelectrochemical effect, also in closed cells. Subtract in cells with circulating electrolyte the thermoelectrochemical and thermoelectromechanical effect. The theoretical models of excess heat are no longer encountering the difficulty of explaining the excess heat observed experimentally. We saw the linear graphs both in these two presentations, in slides number 13 the first time and number 9 the second time, and all kinds of. And so the important theoretical progress that has been obtained also by the presentations that we've seen here and by previous works and experimental work, all the nuclear evidence that we have today, it is a large amount of evidence. All are no longer be derided, or it's no longer possible to claim that this is not science. And the critics ridiculing experimentalists who reported the excess heat had better be looking for explaining the phenomenon. I'm speaking about Huizenga. I'm speaking about that author. I forget these guys very easily. Tom George gave me a copy of Huizenga's book. And in it, for instance, also the bold work of Verbos the NSF program director who organized the cold fusion conference against all ridicule, yes, is lauded. Thank you very much. And I just want to say it is important. This unifies, understanding the excess heat correctly unifies the scientific community again. It is not an argument for reducing funding, but it is an argument for strongly increasing funding. It is as if starting to work now with optical tweezers rather than with simply a pair of tweezers, mechanical tweezers on molecules, you know. Okay, I thank you for your attention, and please come up with questions.
Peter, just a couple of comments on current. I mean, your interpretation of what Ed has said and what I have said is not correct. The excess power increases linearly with current above a very significant non-zero current threshold, continues to increase with current and then hits a maximum and doesn't increase any further. So there is a linear region, but it's only part of the phenomena. That we're interested in it because for a certain range we can increase the excess power. The other point, of course, is that
I've seen graphs, of course, in the past that were totally linear also.
It's not. It's not. No, I've done the experiments. It's not totally linear.
But you are right. I mentioned this. It's
Okay.
due to the fact that we have a characteristic of loading. It's first an exothermic process. Later on it becomes an endothermic process. Then it becomes unstable.
All right,
and
but
then you see, Ponce Fleischmann reported when it fell through the floor, you know. Do you remember the incident?
well, I just wanted to make sure that you used the
I understand, I agree completely.
If you're going to
that
quote
there is
me,
no
quote
perfect
me right.
linearity there.
Yeah.
Yes.
The second is that excess power has been observed in many places and many experiments, including my laboratory, in which no current was present at all.
Yes, because the thing was format. The thing,
No.
The energy already was in.
No, these are gas loading experiments. No current.
Hydrogen, right?
No current was ever applied to. No current was ever applied to the experiment.
Never applied, but there must have been deuterium there.
Yes, there was deuterium.
So if there was deuterium, then it was loaded somehow in there, right? It may have been loaded through other methods. You don't need to apply a current to load these gases. Ahlefeld and myself, we all like that guy. We've been working with them and did these phase transitions. Quite interesting. Many body phenomena. Thank you. But this is outstanding work that you've done. Both McCuber and you and all the guys. I fault only the guys who are disregarding experimental data. That's what I fault. And I think from now on we have the chance to get, in a legitimate way, to get funding from the Department of Energy, from the Department of Defense, and from all their energies. We hope that this is going to lead to an appreciation of the cold fusion effects as legitimate science.
Thank you very much. Thank you. And just kind of on a topic too, when there's gas loading of palladium, if you apply a pressure P and measure the amount of volume that has to flow into the system to keep the pressure constant, P times dV is a measure, if you will, of the work done to do the loading. So there was some discussion before in the conference about, a comparison of what is the effective energy of loading, if you will, in the gas pressure loading cells. I would think that something like that would be the equivalent energy. But now that we come to the end of this, I really appreciate everyone's participation.